pleasure to It's a pleasure to have you all here at our second Disaster Mobility Data Network meeting. Our objective is to foster and strengthen research related to the use of mobility data for disaster risk management. We're looking to share cutting-edge scientific knowledge, use cases, robust policy insights, latest trends and challenges around the use of mobility data. The agenda for today is the following. First, we'll have Dr. Caroline Buckee talk about thinking clearly about social aspects of infectious disease transmission, followed by Takahiro Yabe talking of post-disaster population displacements and recovery analysis using human mobility data. Before we begin, I would like to make some comments on housekeeping. During the presentations, please write any questions in the chat and we will address them at the end of each presentation. We will have time at the end for further discussion. Please feel free to come off mute to contribute during the Q&A at the end. Remind that all the meetings will be recorded and uploaded to the CrisisReady YouTube channel. Without further ado, I would like to introduce our first speaker. Dr. Caroline received her PhD from the University of Oxford. As a Sir Henry Wellcome postdoctoral fellow, she analyzed clinical and epidemiological aspects of malaria. This work led to a fellowship at the Santa Fe Institute, where she developed theoretical approaches to understand malaria parasite evolution and ecology. In 2013, she was named one of the MIT's Tech Review's 35 Innovators Under 35, a CNN Top 10 Thinkers, and Foreign Policy Magazine Global Thinker. Her work has appeared in high-profile scientific journals such as Nature, Science, and PNAS, as well as being featured in popular press, including CNN, Voice of America, and ABC. Caroline, the floor is yours. I think you can share a screen now.
Okay, thank you. Hi, everyone, and thank you for joining us. I guess today the title of my talk is a little bit, may seem tangential to what everybody is interested here, but I hope that I will explain. It says that the host has disabled participant screen sharing, so I'm not sure I can share my screen, Andrea.
Oh, let me.
So I'm an infectious disease epidemiologist, and epidemics are a particular kind of disaster, and they require an understanding of a particular kind of mobility and human migration. So I'm going to talk a little bit at the beginning about, about epidemiology and how we think about human migration in the context of epidemiology, and that's what these social aspects are. We're talking about human behavior in terms of contact rates, and then talk about some of the technologies that everyone here is interested in terms of how we measure and monitor those things and put them into models of infectious disease. So most of this talk will be focused around a paper that came out very recently. It was co-authored by Abdisalam Noor and Lisa Sattenspiel, and we were really, this was part of an issue in Nature, thinking about how social sciences intersect with some other kind of issues like infectious diseases and epidemics. And the title here, Thinking Clearly, comes from a quote from Bob May, who passed away recently. And he talks about how the virtue of mathematical modeling in this context is that it's a way of thinking clearly about how the basic assumptions of your model are related to empirical facts. And I think it's really important as we think through some of the data streams that we are using now to understand population dynamics and how people move around, really relating it back to what we're assuming and thinking clearly about what that data means for some of the subjects that we're interested in. So I would distinguish between three different kind of ways that mathematical models are used in infectious disease epidemiology. One way is to try to understand the mechanisms by which infection spreads. And so, for example, there have been models looking at SARS-CoV-2 dynamics and trying to understand how assumptions to do with immunity or seasonality might impact long-term dynamics. We might also be interested in estimating something like the age-specific mortality rate. That's a way that models are used. Also is going to include some of these methods for understanding how people are behaving, and I'll explain that in a bit. And then ultimately, sometimes we want to make specific predictions. And I think this is where infectious disease epi kind of overlaps with some of the interests here, which is what might we expect in the short term, and what does human movement and sort of human population behavior mean for some of our predictive models in that context. So just to take you back, for those of you that aren't in epidemiology, the basic framework for forecasting or understanding how diseases spread often comes back to this basic framework, which is a susceptible, infectious, recovered model, which of course the world is now familiar with since the last 18 months, where you put people into one of these compartments with respect to an infection, and then you try and understand how a disease will spread. And the important part here is that the rate at which people become infected, so all of the predictions that you might have seen in the news about how many cases to expect, most of those predictions come back to a model like this, and the driving forces in terms of how many people will be infected in some time period relates to the probability of infection given contact and the contact rate per unit time. And it's this second variable, the contacts per unit time, that actually brings in all of these social, behavioral, movement patterns that kind of underlie the dynamics that we see in the population. So in theory, we can use these models to understand how epidemics spread. And we get a nice curve like this, where the susceptible population is used up, we get an epidemic peak, and then the emergence of immune people in our population. And under these kind of simplistic frameworks, the epidemic runs out because susceptibles are depleted, and that ends the epidemic. So in a basic framework, you have a fixed contact rate over time. So people's behavior doesn't change. How many people you come into contact with remains the same over that time period. In reality, of course, we've seen for the coronavirus epidemics that look like this, and this is data from Massachusetts, and we see these multiple extended prolonged peaks that don't really look like this sharp peak here. And the reason is to do with human behavior and mobility patterns. We don't have random mixing, and we have a time varying contact rate dependent on policy changes as well as human behavior and how people are moving around in their communities and between communities. So this susceptible depletion is actually heterogeneous and quite local in many cases. And so when we think about this on a local scale, some of the human behavioral aspects that we can start to measure using these new data streams are on a kind of neighborhood basis and within a city, right? So people, the drivers of epidemics, the contact rates that drive the spread of disease are to do with people visiting their friends and families, going to religious and social gatherings, moving around for work, and so on. Some of those seek treatment for a disease, and then we get surveillance data from that. And some of the data that we use can be developed into a framework to understand the spread of disease between individuals. So this picture here shows each of these dots is an individual in a network, and it shows how disease is spreading from one person to the other. So these highly localized contacts are what's underlying some of these population level dynamics that we can measure. Some of the most important social aspects of disease that sort of define how a disease will spread is that many populations are structured by age. And so there have been a lot of diary studies where in different cultures this is going to look different, but basically people of different age groups are asked who they interact with each day to get an understanding of how the contact rate is structured. And what you can see from these two pictures, for example, is that Italy and Germany have very different contact rates. So this is the age of the person answering the questions on the x-axis, the age of their contacts on the y-axis, and the heat map, the gray to red, just shows the frequency of those contact patterns. And so you can see there's a diagonal here because people tend to interact with people of their own age. In Italy, there's much more mixing between age groups, and in Germany, there's less. And so there are distinct differences between populations in these assortative mixing patterns. And that's really going to have an important impact on how disease is going to spread. And of course, as we start to survey different countries around the world, we start to see different patterns of age assortative mixing, and that has an impact on our models as well. And specifically, when we think about the data streams that you're all interested in and the movement patterns, we have to ask ourselves, who is in our data? How biased is the data that we're using to try to understand how people are moving around, who is captured, who is not, and how is that going to impact the epidemic trajectory? So I think that there are two ways that we can think about sort of mobility and migration and how that impacts the spread of an epidemic. The first is kind of on a local scale. So there's a population at risk, and we might want to know, how many people are coming into that population to bring infection, and how many people who are infected are taking that outbreak and spreading it elsewhere. And so, we've talked about these local contact patterns to do with, work and home movements, but there's also seasonal and long distance travel, and that impacts the spatial spread of a disease over larger spatial scales. For a long time, we really had not very many data streams to parameterize this kind of these parameters in our models. We relied on things like census data, some cross-border information, and travel history surveys. Now, if you think about this on an axis of space and time, here on the x-axis we have local to international movements. On the y-axis we have very short-range movement patterns all the way up to long-term migration. A lot of these data streams were not very satisfactory for a rapid and acute emergency like an epidemic or like a natural disaster and so on. They were on the time scale of years, and they were on a spatial scale that was quite large. But now that we have access to mobile phone data, all different kinds of mobile phone data, not just from social media, but also from mobile operators, and even on a small scale from some small scale studies, we can start to pick up across many different scales of space and time the mobility patterns that are underlying these contact rates, both within and between populations. So at the beginning in my group, we've been working on how to use this data for epidemic modeling for some time. At the beginning of the COVID-19 pandemic, we realized that although policymakers wanted to understand these kinds of human behaviors on a local and regional and even international level and use them in their decision making, and despite the fact that companies were very willing to put out some of this data from their own users, there was this big gap in translational capacity. So policymakers wanted the data, but they didn't really understand how to translate it in a way that made sense for their specific decisions. And so Andrew Schroeder and Sajid Balsari, who are on the call, and I, we've been working for the last year and a half to help bring these data in a policy relevant way to the people that have to make decisions during this COVID-19 crisis. And a lot of that was not necessarily mathematical modeling for epidemics, but certainly about local and regional population mobility that would underlie transmission and be important for policy. And regardless of the kind of data that we looked at the beginning of the epidemic, we saw a broad concordance in the relationship between the mobility patterns measured by these mobile phones and the epidemic itself. And so if you look in the US, this is from a paper from Lauren Gardner's group, and they looked at mobility patterns over time. This is from 2020. And what you saw, this y-axis, it doesn't really matter what it is, it's just kind of relative movement. What you saw across the US was that in the middle of March of last year, there was a dramatic drop in how people were moving around. Regardless of local policies, there was a general population level drop. And that was when the state of emergency was declared. So we saw rapid reductions in transmission because of this behavioral change across the country. And of course, the contagiousness of the disease hadn't changed at all, right? It was all in this contact rate. So for epidemic modelers, we were trying to understand how to translate some of these mobility data sets into a meaningful contact rate parameter that we could put into the models to make predictions. In fact, there are large-scale mobility patterns that are important drivers of disease around the world. This is a picture from a mobile operator in Bangladesh that shows movement patterns of people around the Eid holiday. And you can see people leaving Dhaka here in the center of the country and going to rural areas and then coming back at the end of Eid. So we know that travel for holidays is a major driver of infectious disease around the world in the flu season, for example. And we've also seen this in COVID-19, actually. We've seen holiday travel be a major driver for the spread of infection. So now we're starting to be able to measure these big asymmetric patterns of disease spread that are related to these behavioral and social and cultural events like holidays. This just shows a heat map. Here you can see over time the Eid holidays are highlighted here with these two vertical bars. And what you're looking at is the travel of people out of Dhaka to other parts of the country over time. So you can see weekend peaks, and then during the holiday, you see a massive outward movements to the rural areas. In fact, this is a general phenomenon around the world. So we see, for example, this is from Namibia. We see very distinct seasonal peaks. Sometimes this is to do with seasonality in agriculture. Sometimes it's to do with holidays, but it's a general feature around the world that we have to take into account when we're thinking about mass movements of people and what that means for the spread of epidemics. Similarly, this is a picture of pastoralist movements in the Sahel region. These are extremely relevant for the spread of diseases like malaria. They're very hard to capture in our standard models. And as of now, these cross-border movements are also difficult to capture in these digital data streams. So I think cross-border movement remains very difficult to deal with in terms of these mobile phone data sets because they're largely national rather than international. So we have large seasonal migration patterns that we know are important drivers of disease, and we need to integrate into our endemic pathogen models. And then we have these difficult movement patterns that we actually are not well able to capture even with digital data streams. Understanding the reasons for travel and some of the different social aspects is going to be really important, I think, in coming years, because there are very different social reasons among different demographic groups. So we have these large data sets, but often they capture different demographics in different ways and sometimes not at all. So this is a survey study in Bangladesh showing different travel patterns for men and women. And this is from malaria patients in the Chittagong region of the country. And what you can see is that men tend to travel very far compared to women. So we have to be quite careful when we're dealing with these large scale data sets. We need to be careful about inferring things that are very specific. And we need to really start, I think, being conscious about quantifying uncertainty as well as demographic biases. This is just to show that the distance traveled in kilometers is not necessarily just a gender specific thing, but also related to reasons for traveling. So different agricultural workers, business workers, military workers, and so on might be traveling for different reasons. It's quite hard to accommodate that within some of our epidemic model frameworks. And then the last thing that I think is important, that may be important for many disasters actually, is that when we try to make predictive models about how people might move or behave in a different situation, we have to be aware that there are feedbacks between perceived risk and what people actually do. So this is just an SIR model like the one I showed you at the beginning, but here there's a feedback between the human behavior, which is modeled through the contact rate that we've been discussing, and the disease itself. So here you can see these multiple peaks, and they occur because as the disease increases, people start to reduce their contact rate out of fear. And then when the disease goes away a bit, people return to normal and you get a second wave. And of course, that's exactly what we've seen with COVID-19. But I think the reaction to different types of risks and the ability to make a predictive model to make sense of what people might do is still something that we need to think about very hard. So I think I'm probably a bit running out of time, but just to say that the response to the epidemic has also shown some interesting, almost, I would say, universal behaviors. So we looked at movement patterns in different parts of the world in response to lockdowns. And so here we're comparing France, India, and Spain. And in all of these places, there was a lockdown announced. And what we saw was massive urban to rural migration. So these lines here are colored according to their nightlight category. So the yellow ones are very urban. And as you get dark, you get more and more rural. And you're looking at the percentage of change in the Facebook population in these different areas. And when lockdowns were announced, essentially the urban areas emptied and the rural areas filled up as people moved out of the city. And this type of response has actually been found over, for decades and decades in response to epidemic threats. People tend to leave urban areas and go to the countryside. And so again, we can start to use these big data streams to understand these mass migration events, even if we can't necessarily drill down into all of the detailed demographic differences. And of course, the reasons and the demographics that are leaving urban areas in France may be very different from the demographics of people who are leaving urban areas in India. Okay, so I'm just going to make one last comment that might be relevant. So one of the things in the epidemiological models, at least, is that even if we have really good mobility data and we can start to make sense of the human behavioral aspects, sometimes the epidemiological data is limiting. So this was a seroprevalence survey looking for who had antibodies to COVID-19 in Mumbai and stratified by slum and non-slum regions. And what they found was that in the non-slum regions, seroprevalence was quite low. This was as of last August, whereas in the slum regions, seroprevalence was quite high. This was despite the fact that there hadn't been very many cases logged. So what that means is that the case counts have not been very reliable, and they've been biased in a very systematic way. And so when we think about epidemic modeling anyway, the human behavior is one part, but if we're trying to fit models and make predictions, we have to be aware as well where the epidemiological data is coming from, just as we have to be aware where the mobility data is coming from. And I would just end by saying that I think the importance of understanding the biases and these very specific contact rates increases as we go from these kind of abstract mechanistic models to making specific predictions. And so I think it's very challenging to make predictive models around human behavior. And that's one of the things that will be an important priority for research in the future. So I'm going to stop there. And I think I'm not too far over time, Andrea, but thank you. And I will take any questions, I think, afterwards.
No, we're good with time, Caroline. And actually, if there is anyone that has questions of your presentation, now is the moment before we move further. Well, actually, I do have a question. Meanwhile, somebody asked. And my question is related now to the gaps in data and the biases that you mentioned. What do you think that would be the best strategy, or how we could refine this data to make better predictions?
Predictions about what?
Over the spread of diseases.
So I think the importance is going to be to complement some of these big data streams with more traditional social science approaches. So we have to complement the sort of large scale analytics with surveys, making sure we're not missing people, starting to do systematic comparisons between different types of data, and things like that, and being very careful and explicit about uncertainties. I also think that there is some responsibility among data providers to give some indication about uncertainty and some sense of representativeness, so that when it goes through the kind of research pipeline and into the model, we have some sense of how much we can rely on that data. Because I think that's really key at the moment. Some data providers are not very clear about exactly how representative their data is. And it doesn't have to be in a way that's risking identifiable data or anything like that, but in general terms, we do need to know about uncertainty and representativeness.
Perfect, thank you very much. Is there anyone that had questions in the floor? We could also go back at the end of the other presentation. If not, I would like to give the floor now to Takahiro Yabe. Thank you, Caroline. Thank you very much. So Takahiro Yabe, he is a data scientist consultant at the Global Facility for Disaster Reduction and Recovery from World Bank. He works on using smartphone location data for urban disaster risk management operations, including post-disaster evacuation, displacement, and recovery analysis. Taka obtained his PhD from Purdue University this August, and he will join the MIT Media Lab Human Dynamics Group as a postdoc this fall. His research interests lie at the intersection of disaster risk reduction, mobility, data analytics, and computational social science. Thank you, Taka. Now the screen is yours.
Thank you, Andy. Thank you for your introduction. So hello, everyone. I'm Taka. I'm a data science consultant at the Global Facility for Disaster Reduction and Recovery, the GFDRR, the World Bank. And as Andy mentioned, I'll be joining the MIT Media Lab from September, which is very exciting for me. But today I'll focus on what we've been doing at GFDRR. We've been pushing for the use case of mobility data for various project operations in disaster management, urban planning, and transport analysis across different countries. And Mexico City is one of them, because Mexico City had this large earthquake called the Puebla earthquake back in 2017. And we've been trying to use mobility data to understand how people get displaced and how do people come back? How do they return or recover after the shock? So I'll start off with the case study of Mexico City, and then I'll expand into other types of disasters that I've been looking at during my PhD, including mega hurricanes in the US, Puerto Rico, and also tsunami in Japan, where I'm from, and other minor disasters as well. So we go to the next. Okay, so call data records, or CDR, have been used for, I think, over 10 years now, and we're very successful in informing population displacements in notably Haiti and Nepal 10 years back, or five to 10 years back. But recently we've been seeing this emergence of novel smartphone GPS location data, which are relatively more spatially and temporally accurate or granular. So spatial resolution is about 50 meters, and temporal resolution, we have around 50 to 100 location pings per day. And within the bank, we have this bank-wide MOU called the Development Data Partnership, which enables us to relatively easily access data from various data companies that own mobility data. So we've been trying to expand and scale up our analysis within the bank for use cases including disaster response and recovery, but also for, in general, urban development as well, so spatial analysis and transportation planning. So the disaster that I mentioned earlier, the Puebla earthquake, was magnitude 7.0 earthquake that affected central Mexico and areas of Puebla. And so I'll be talking about this earthquake mainly in this talk. So I just want to quickly go over a typical kind of location data analysis flow, workflow. I think it's really important to first look at the data itself and clean the data sets. So we want to remove users who are not living in the area, like tourists, or users with very little number of pings or observations within the data set. So users that are only observed once every day, or only across like 3 days across the entire 30 days of data, for example. So we look at number of days covered and the number of data per user typically, and we try to limit the user base that we work with. And then, as Caroline mentioned, I think it's really, really important to look at representativeness of the data set. So we want to know if the mobile phone user sample is representative of the population, actual population. So one typical analysis we do before getting into all of the analysis is to look at the correlation between the census population and the number of mobile phone users in any kind of given admin level. So here I'm showing the number of mobile phone users versus the number of census population in each localidades level. So that's kind of like a census block or census tract level in the US. And we see here that there's really nice agreements, high correlation between these two data sets, right? And we here conclude that mobile phone data is somewhat representative of the entire population. But then this is just looking at the number of people, but there's many other ways to look at representativeness. Like you can compare the sampling rates between poor versus rich and see if there's any bias in the data set, maybe race, gender. Those could be other variables that we can potentially look at. So after checking the representativeness check, we conduct all the displacement analysis using the mobile phone data. And today I'll be talking about displacement dynamics, recovery curves after the disaster, and also looking at trying to estimate how businesses recover after disasters using mobility data, and also public services like hospitals and schools, etc. So one of the first things we do when we get access to this data set, mobility data, is to estimate home and office locations. So this can be done in various ways, but typically what we do is we take the nighttime stay points for each user, and then we cluster them using any kind of clustering algorithm like mean shift clustering or k-means or whatever. And we can weight them by how long they stay in each location, or we can do all these things. But ultimately, we want to validate the population distribution using census information as shown in the previous slide. For office locations, we do the same thing, but with daytime stay points, right? But we can induce some rules like an individual has to visit his or her home, office location more than 3 times a week or something like that, and try to filter out people who are just going to their favorite restaurants or something during the day. And to inspect whether we see the disaster had a severe impact on population movement, we can first look at whether there's anomalies in population dynamics after the disaster. So typically what we do is we take a 30-day data set of population dynamic maps, and then we compute the average and variation of these maps using the pre-disaster baseline. A simple score would be the z-score, which is the difference from the mean divided by the standard deviation to obtain these kind of population anomaly maps. And this is from Mexico City right after the Puebla earthquake. And clearly you see this blue patch in the middle showing that there was significant displacement from central Mexico City on the night of the Puebla earthquake. And we can do this not just for one slice of time, but we can do this for a long period of time, even before, during, and after the disaster. So this, for each individual, we label him or her as displaced if an individual stayed the night away from their home area, and we compute the disaster displacement percentage, which is the excess displacement rates from the baseline. And baseline includes all of the non-disaster displacement which occurs because sometimes we feel like staying in our friend's house, we feel like staying the night in a bar, or we have this regular kind of, it's not displacement, but from the data set, it becomes detected as a displacement. So we have to cancel out that natural displacement effects. And we do that by taking displacement curves from areas that were not affected by the disaster, but physically close to the area which was hit. So here, this is showing the disaster displacement percentage across before and after the earthquake. You can see that right after the earthquake, we had around 3 to 4% of displaced population, and that it gradually decreased over the 2-3 weeks that we had in our data sets. And during my PhD, in fact, I looked at different types of disasters as well, not just earthquakes. So we looked at hurricanes in the US, Hurricane Maria, Irma. We looked at the Tohoku tsunami in Japan, where I'm from, the Kinigawa flood, which is a minor flood that occurred in Japan. And similar to the curve that we saw in Mexico City, we found that despite the different initial starting points, long-term displacement rates, and the recovery speed, all of these population displacement recovery patterns resemble an exponential decay, which I think scientifically, I think it's interesting, and also operationally could be very useful, because once you get the initial few data points, you can try to predict which Caroline mentioned, I agree it's really difficult to, even in the disaster context, to predict how people will move, when they will come back after a disaster. This general rule could be useful in predicting that. So if you look at Hurricane Maria, you see that 60% of the people were displaced right after the hurricane. And then even after 5 months, you see around 25 to 30% of the people still being displaced. This was for the aggregate whole island of Puerto Rico. But once you look into different communities, you start to realize that different communities have really, really distinct recovery curves as well, which is very interesting. So in the study, we tried to explain the variance that exists across different communities and found that obviously disaster intensity is important. So the amount of housing damage you have in a community. Also community characteristics like population density, median income, which I'll talk about in the next slide, and also infrastructure, how well the community is able to repair their infrastructure is very important. And also some interesting insights on urban networks. So the plot on the top right shows how two very socioeconomically similar cities like Ciales and Guanica had distinct recovery speed, because Ciales was much closer to the San Juan, which is the capital area, capital city of Puerto Rico. So cities that are closer to bigger cities tend to recover faster. And also social ties were important. So cities that have a lot of people going back and forth between big cities before the disaster had quicker recovery in Puerto Rico. So going back to the Mexico City case, we found that poverty was a strong determinant of displacement rates. So we took the correlation between poverty index, which we developed from a bunch of different composite indexes, like vehicle ownership, refrigerator ownership, whether they have a computer or not, and access to services like education and health. And we see this negative correlation, meaning that poor people were not able to be displaced or had lower displacement rates. And this is because poor people lack both the transport and financial means to vacate these dangerous areas, and are more likely to shelter in place or evacuate to other unsafe zones. So these are all the analysis that we can do, just a subset of what we can do, but key insights that we can obtain from mobility data for displacement and return movements. And another chunk of analysis that I'd like to introduce to you today is to combine the human mobility data with point of interest data, which has been done in non-disaster use cases a lot, but particularly in disasters, I think it can be very useful in understanding how urban systems recover in general. So we take data, POI data from OpenStreetMap, and we compute the visits and catchment dynamics using mobility data. So we can answer questions like how many people are visiting, for example, this hospital, how much was the disruptions caused by disaster, how quickly did it recover, all of these things we can quantify. And also a good thing about mobility data is that we can also understand who are visiting this hospital. So is it the wealthy people who are visiting this hospital, or is it more the poor? And where do they come from? How long do they travel? All of these things we can extract from this data. I'll show an example of what we can do from a Walmart in San Juan, Puerto Rico. We can estimate a proxy of economic impacts to businesses, be it visits to these stores using mobile phone data. So as you all know, San Juan, Puerto Rico was had the impact of Hurricane Irma and Maria, 2 hurricanes in a row. Maria was the more significant, but here I'm showing the number of visits to this Walmart in gray. This is the data. And then using a Bayesian structural time series model, we predicted what if the disaster didn't occur, how much foot traffic this Walmart would have had. So you can see the blue kind of ignores these disasters and goes on beyond the post-disaster period. So we estimate this trend based on the pre-disaster trends and also Walmarts in other locations across the US. And then we take the difference between the two to understand the impact of the disaster. So you can see clearly that before the disaster, we had an increase in people visiting Walmart, mainly to prepare for the hurricane. But then you have this more long-term, persistent deficit in the number of visits, showing the post-disaster decrease. And you can do this for all of any kind of POI that you have in the data set. So what we did was we looked at thousands of POIs from different categories in different regions in Puerto Rico. So, and we ran a regression on the total impact that the business sustained based on, and we tried to explain that using various variables. And this is showing how different impacts were inflicted based on business sectors. So you see gas stations, hotels, and building material stores having a positive impact, which means that more people started visiting these POIs after a disaster, which is kind of intuitive because a lot of people evacuated hotels, people need gas, and also people need to rebuild their houses. And then you see, on the other hand, you see these hospitals, supermarkets, universities, which had a significant reduction in the amount of visits they had. And you also see a very stark urban-rural disparity. So you see that rural or businesses in rural areas took much more time to recover compared to urban areas. And also the sizes of businesses were significant. So small-sized businesses tend to struggle more and for longer periods of time compared to larger businesses like a Walmart. So I think I don't have much more time, so I'll talk about some points to use to some of our recent works. So recently, I had the pleasure of working with Nick Jones from the World Bank, Marta Gonzalez from UC Berkeley, and Professor Sobral and the Kasuri at Purdue on looking at various types of applications of mobility data for disasters. And we did a review article on natural hazards and epidemics with the help of Professor Gonzalez. So you can see that the number of papers that use human mobility data and mobile phones are rapidly increasing, and we thought this was a really nice opportunity to kind of organize the research that has been going on. So you have the disaster risk management cycle, and in each phase of the cycle, we see very useful applications of mobility data. So if you're interested, please take a look and let us know if you have any comments. It's still an archive paper. So, and all of this analysis that I showed you today can be done very easily using an open source toolkit called Mobilekit. We developed this at the World Bank, Mindearth, which is a company in Switzerland, and Purdue University co-developed this toolkit. There's a really nice read the docs, so it tells you what each function does and the details of it. And most importantly, you can really easily pip install Mobilekit to your local environment. And it uses Dask, so you don't have to have like a cluster computing architecture. You just need to have a laptop, and works pretty well on a laptop or desktop computer. So with that, I'd like to wrap up by saying GPS mobility data has immense potential. As I showed you a couple of examples today, in various disaster risk management applications. And I'd like to ask you to please test Mobilekit with your mobility data. I'd like to thank all the collaborators. I think Maham is joining the call today. And Nick from the World Bank, my PhD supervisor, Professor Kasuri, and Enrico, who developed the Mobilekit toolkit. So with that, thank you very much. And I'd like to take any questions.
Thank you very much, Taka.
Thank you.
So we open the floor for the questions.
Hi, I have a quick question regarding how we can use mobility data to, let's say, try to predict mobility, as was going to Caroline's point, for, let's say, for the opening of schools. So regarding school, faculty, teachers, and people working in that area. I'm trying to figure out, like, there are a lot of really great applications that you showed for supermarkets and various other institutions, businesses and whatnot, but how can we utilize this in the specific context of, let's say, schools, and how that can inform our decision-making for opening certain schools in certain parts of a country, or keeping them closed, or having like a hybrid system, and to what degree we should keep it hybrid, so on and so forth.
Is that a
This
question
is
for Caroline?
addressed to both Dr. Yabe and Caroline. Since Caroline had mentioned the predictive stuff, and Dr.
Oh,
Yabe
okay.
did this.
Yeah, sorry, I thought that was for you, Taka.
Okay.
So I think, well, one obvious thing to do is to just compare, just to have different time periods where you have baseline behaviors, and use the same, right? So you just look at time windows where school term is going, and you compare it to time windows where school is not going, and you just do some kind of simple comparative analyses. Obviously, children don't, for the most part, children don't have phones. So what you would look for in those kinds of comparative analyses would be sort of the sort of more population level dynamic impact of opening schools. I think within universities and higher level, where you do have people that have phones, you can do a bunch of specific things. And actually in universities, there are initiatives where people have an opt-in kind of approach to looking at quite fine scale movement patterns using GPS and Bluetooth and so on. And some of the data on some of the fine scale movement patterns comes from sort of observing university students. But I think in terms of the societal level impact, it's always, you need to incorporate some of the age structured mixing patterns. You need to know about household structures for epidemics anyway, because the household structures are what is going to determine the impact that school transmission might have on the wider community. So you could use data layers like catchment areas for different school districts, think about trying to layer on data sets about households, generalized household structures, and then combine some of these comparative data sets where you look during school and outside of school. But I think it's always going to be quite challenging where you have a systematic absence of data from a particular demographic group of interest. And so to some extent, there are some inherent limitations with some of these data sets. So you have to kind of cobble together other things that you know about that system and use inference and models to make up the gaps, essentially. I don't know if you have more to add, Taka.
Yeah, if I can add one point from a disaster kind of perspective. When we looked at number of people who are visiting schools in Mexico City after the earthquake, we found that, in fact, although the schools were closed for a couple of days, we saw an increase in the number of visits, and we were kind of puzzled by that phenomenon. But we found that schools were being used as evacuation shelters. So even if you look at the number of visits to schools, we can't just look at them as just a visit, but we have to think about why the people are visiting these locations. And we can do that by looking at before the disaster, did these people actually visit schools, or are they new people who are visiting schools, which could tell you that those people are indeed evacuating to schools, right? So I just showed the number of visits to Walmart, for example, but we can also look at where these people are coming from, what these people are typically, usually coming to these areas, and try to draw some more insightful insights from that.
Great, thank you so much.
I have one question, but I mean, it's more question about how hard it is to get access to mobile data. So I'm aware that CDR data can be easy to get, but then your analysis, it's more complex and it actually has a time. So you access data from the past. I mean, the question is how hard it is to actually get access to that data to start doing a study on that.
So I would say that CDR data is probably one of the hardest data streams to access because each mobile operator is subject to the regulatory approvals and systems of their country. And so which lays out how the CDRs can be used and under what context. So I think it usually, at least in the past, it has involved a negotiation and really like a lot of approvals and discussions, not only with the regulatory bodies, but also with the data scientists in the company itself to figure out how to do the aggregations in such a way that you protect privacy. So the spatial aggregation, the temporal aggregation has to be discussed with the operator itself before they aggregate it. So CDRs can be tricky. The good thing about them is that they cover dumb phones as well as smartphones. So you have a much broader representative sample of the population. For some of these data sets like the Facebook data, that they've already done the aggregation, they've kind of reached a standardized set of ways that they put the data into a usable format. So that's in many ways easier because you can work with them to get a data sharing agreement, and then they have these standardized maps and things that you can download, and it's in a relatively standardized format. So some of the company data from social media is sometimes actually easier than the mobile operator data itself. I would say we're still in a phase where each company or data provider that you're working with has a slightly different set of rules, a slightly different way of aggregating. And you talked about baselines, so slightly different way of calling the baseline. If you're looking at anomalous movements, then you have to think about what it's compared to. Given that there are seasonal patterns, you want a long baseline so that you know that you're accounting for annual seasonality and things like that. Many data providers don't store data that far back, or they have a particular number of days. So Facebook, I think it's 45 days prior to an event. And so it really is kind of different depending on the type of data you're talking about, and the ease of access is also different, and what you get is different. So I think it really depends, but I wouldn't say it's straightforward, and that's before you get to any of the analytics. This last year and a half, it has got a lot easier, and I think that there's a lot of discussion about how to standardize this in a way that's still useful. But I'd say we're not there yet.
Thank you.
We have a couple of minutes. Does anyone has any questions? No. I would like to thank our speakers. Oh, yes.
Yeah, if nobody else is going, I did have another quick question. So I found the point that Caroline made about integrating feedback between behavior and disease really, really interesting. And I was wondering, like, how does one go about doing that? Like, how do you take into account different behaviors from various different populations and sort of use that to understand disease dynamics? Because the general curve for a single population, the one that she showed, that's very, very interesting, and it's very relevant because we've seen that very much. But how do you sort of try to understand different behaviors from different populations and then figure out disease transmission within those populations, let's say for a specific occupation or a specific area of the country?
Well, I think it's incredibly challenging. And I think that the integration of these types of behavioral responses into the models, I mean, mechanistically, it interacts with the contact rate, right? So in that model, people reacted to disease prevalence, and there was a functional relationship between the contact rate and the disease prevalence that was supposed to represent kind of behavioral response to perceived risk. Of course, it's actually incredibly complex and culturally dependent and context specific, and there's policy, not just human behavior. So I think this is an area of massive research that needs to be done, and specifically to try to think about context specific social science work to try to understand this. It's likely to be very heterogeneous, and it's likely to be quite context dependent. And so rather than making general models that are top down, what we're going to need is a distributed modeling approach, but that requires context specific social inputs to make sense. And I think that's something that we're going to have to grapple with in terms of pandemic preparedness planning for these types of analytical approaches. But it's still, I'd say it's still, there's not one approach that's going to work everywhere. We're just starting to do that in the theory.
Can I add one point about feedbacks? I think that's very, very interesting point. I think in disasters, it's really relevant as well, because if you start looking beyond the response phase, if you start looking to longer term recovery, and people start migrating, because people's movement isn't only affected by the environment, and it also affects the environment as well. Right, so if people get displaced a lot, the public infrastructure in that area would deteriorate. On the other hand, areas that are attracting people, those infrastructure, public, water systems, power grids, they won't be able to cope with that, and that would again have a feedback effect on people's movement decisions. That could drive people out of the area, and we could all have this really complex dynamics over a long period of time. So. And that's really understudied, I think, in the disaster field. And compared to like the SIR or SEIR model in the epidemiology study, there's no such thing in like disaster displacement and population movement. So I think that's a really, really big field of study that we can all kind of as a community go into in the next couple of years. So.
Yeah, very exciting. Thank you so much for your answers.
Thank you.
Thank you, Taka. And we have one more question from Alan.
Good morning. I want to thank you both for the presentation. I think the work you're doing is exceptional. My background, I'm familiar with data analytics. I'm by no stretch of the imagination a data scientist. I'm an attorney, and if I can offer any value, perhaps it would be in working to help negotiate permissions and access to this data. And I was wondering if you could address whether or not how someone in your position goes about negotiating access to the data, and whether or not there might be a place for someone like me to help out in that area.
Well, I can quickly answer. I mean, I think at the moment it's been until COVID-19, it was done on an ad hoc basis, reliant on individuals going and talking and figuring out these data sharing agreements, and it's quite a lengthy, arduous process involving many different types of organizations. When COVID-19 happened, the floodgates opened, especially for social media data. SafeGraph, Facebook, all of these things suddenly became available to different levels. And the concern there was that actually they shouldn't have been sharing quite such detailed data for privacy reasons. And I actually think that in the coming year or so, there's going to be some really serious need to think about legalities and regulations around privacy with these kinds of data sets. At the moment, it's a little bit Wild West. There isn't good legislation, there isn't good legal frameworks and regulatory frameworks for safely handling this kind of data. And the concern that I have is if we don't figure out some really solid legislation, then either it'll risk the breach of privacy that could be potentially harmful, or we risk not using this data at all because the companies decide it's not worth it. So I do think that there's important, quite high-level conversations happening in general around this, and some among this group and legal scholars as well. So I think that it's very pertinent to the conversation. I don't know if, Taka, you want to say more?
No, yeah, I completely agree with Cameron on that point.
Thank you both again.
Thank you very much for everyone. And actually, yes, that's one of our topics that we're going to discuss in further meetings. So I just want to thank you everyone to be here. And here is the agenda for till December. Next session, we'll have the presentation of the white paper, followed by mobility impact analysis in October. Then we'll jump to disaster risk reduction and mobility. And in December, we'll discuss the data ethics and privacy. If you have any questions, doubts, you want to suggest speakers, I'm here for you. So feel free to write me and contact. In the chat, I added the Slack channel that we have for the community where we share more information. Feel free to join. And also, I would like to mention that we're thinking having happy hours. So this meeting is going to be the fourth Thursday of every month, but the second Tuesday of every month at evenings, we want to have like a more informal place to be able to discuss different topics. You'll be getting this information in further weeks. And we're also putting together a repository having papers and more material that you could use, including the Mobilekit. So thank you very much for everyone to join and see you soon. Bye-bye.